Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore the major learning paradigms in modern AI supervised learning, unsupervised learning, and reinforcement learning, and understand how each one teaches machines in a different way.
It's the perfect topic. I mean, these three methods are really the pillars of how machines learn today.
Right.
Everything from, the chatbot on your phone to the system that recommends your next movie. It's all built on one of these ideas.
So when we say an AI learns, what does that actually mean?
Fundamentally, it just means it's finding a mathematical way to map some kind of input text, an image, whatever, to the output or the action that we want.
And it seems like the way it learns really depends on how much help we give it, right? It's not all one single process.
Not at all.
You could almost think of it as, does the machine have a teacher holding its hand? Or is it sort of left alone to find patterns by itself? Or is it learning by just trying things out? Trial and error.
That is a spot-on way to categorize them. And we can start with the one that feels the most like, old-fashioned school, the one with the most guidance.
Supervised learning.
Exactly, supervised learning.
So supervised learning, or SL, it starts from this idea that you already have all the answers. It's built entirely on having pre-labeled training data, basically really well-organized data sets.
Think of it as a student learning vocabulary with, a huge stack of flashcards.
Okay.
For every input, say the word dog in English, the teacher, which is your labeled data, provides the right answer. The French word, chien.
So the machine sees dog, it sees chien.
It sees the pair, and its job is to look at thousands, maybe millions of these pairs and try to figure out the underlying rule for translation.
So it's not just memorizing the flashcard. It's building a predictive model from them.
Precisely. It's not memorization. The algorithm makes a guess, and if it's wrong, if it guesses chat instead of chant, it measures that error. Then it adjusts its internal numbers, its parameters, just a tiny bit to reduce that error next time.
And it does this over and over again.
Over and over. And that iterative process is what we call function approximation. It's just a fancy way of saying it's learning the complex mathematical function that connects the inputs to the outputs.
In the old days, that might have been a simple line on a graph.
Yeah, a linear regression. But today, it's almost always a massive neural network which can learn these incredibly complex, nonlinear relationships. These mappings are foundational. Even in really complex systems, you'll often find a supervised model at the core doing some basic task.
That sounds incredibly powerful, but it also sounds like you're completely dependent on your training data.
You are.
And that's the big catch with supervised learning, isn't it? The massive cost and difficulty of creating those perfect labeled data sets.
It is absolutely the Achilles heel. The models can be stunningly accurate, but they are totally dependent on having that perfect data, and the cost of manual annotation can be just astronomical.
Take something really specialized, like training an AI to summarize computer code.
Yeah, that's a great example. It's way more complex than just, spotting a cat in a photo.
Right.
To train that kind of model, you need actual software engineers, domain experts to go through thousands of code snippets and write a good, concise summary for each one. Then you label that pair.
That's thousands of hours of very expensive expert time.
It is. And the moment you want to scale that up, the cost just explodes.
It's not just the cost, right? It's also that the real world is messy. For something like, say, fault detection in a factory, your data is not going to be perfect.
It's not. You have a huge problem with what we call a lack of real-world faulty samples.
Yeah.
If your machine works correctly 99.9% of the time, then almost all your data describes normal operation.
So how does a model learn to spot the 0.1% of the time that something breaks?
It struggles. It really does. This is the class imbalance problem. The algorithm can actually get 99.9% accuracy just by guessing everything is normal every single time.
Which looks great on a report, but is completely useless in the real world.
Useless in a crisis, yeah. So supervised learning really shines in classification tasks where you can get good, balanced, labeled data.
Like in corporate security? That seems like a good fit.
A prime example. Insider threat defense in cybersecurity is a perfect use case for this. The algorithm is trained on historical data, logs of user behavior that were either benign or later confirmed to be malicious.
But how do you structure that data? It's not just a simple text file, is it?
No, it's highly structured. Researchers will take raw system logs, login times, files access, commands someone typed, and connect all these events into a kind of graph.
A map of user activity.
Exactly. Then they extract features from that graph. Things like, did this user access files at 3 a.m.? Or did they run a sequence of commands that looks like a known hacking script? These features are then fed into the supervised model.
And it learns to classify new activity as either normal or potential threat.
It's taking all that chaos and turning it into a very clear prediction based on the patterns it learned from the labeled data.
Okay, that makes total sense when you have a teacher, when you have those labels. But what happens when you don't? When you're just faced with this mountain of raw data and you have no idea what to even look for?
Well, that's the perfect bridge to our second paradigm, because that's exactly the problem it was designed to solve.
Unsupervised learning.
This is the radical shift. The system is basically thrown into the deep end with a ton of raw, unlabeled data.
And its job is just, what? Find something interesting.
Pretty much. Its mission is to discover the inherent structure, the patterns, the relationships, all without any predefined answers or categories. There's no teacher.
I like to think of it like a geologist looking at layers of rock.
That's a great analogy.
They don't have a label that says, this is limestone. They look at the texture, the density, the relationships between the layers, and they figure out the underlying structure of how it was all formed.
That's it, exactly. The machine's goal is pure discovery. And crucially, this approach is explicitly used to handle the very problems that cripple supervised learning.
Like the imbalanced data we just talked about.
Right. Since it's not trying to predict a specific label, it doesn't care if one group is way bigger than another. It's just trying to find the natural groupings in the data.
So what are the tools it uses to do this? What's in the detective's toolkit?
The main tools are clustering techniques. K-means is probably the most foundational one.
How does that work?
It tries to partition all the data into, let's say, K different groups. It does this based on how close each data point is to a group's center, or its centroid. The algorithm just keeps moving those center points around until the groups are as tight and distinct as possible.
Okay, so that's for grouping. I've also heard a lot about PCA, or principal component analysis. Is that the same thing?
It's related, but a bit different. PCA isn't just about grouping, it's about simplifying. It's what we call a dimensionality reduction technique.
So making the data easier to look at.
Exactly. Imagine your data set has 500 different columns, 500 features. A lot of those are probably redundant or telling you the same thing. PCA finds the new axes, the principal components, that capture the most important information, the most variance.
So you could take 500 features and boil them down to maybe 5 that explain most of what's going on.
And that makes everything downstream so much easier. Then for anomaly detection, which we mentioned earlier, there are specific tools for that too.
Right, for finding the weird stuff.
Isolation force is a really clever one. Unlike K-means, which groups similar things together, isolation force tries to isolate the outliers. It finds that strange, rare data points are much easier to separate from the pack than the normal ones that are all clumped together.
Let's bring this back to that fault detection problem, which was so tough for supervised learning. How would unsupervised learning tackle something like a tram's air conditioning unit?
It's a perfect fit. Researchers use these clustering techniques to first build a model of what normal looks like. They'll take a massive data set, like the UCI Metro PT3 data set.
Millions of data points, I assume.
Millions. Temperature, pressure, vibration, motor current, everything. They use K-means, or PCA, to model the system when it's working perfectly.
So they have a digital fingerprint of a healthy machine.
A perfect fingerprint. Then, if a new set of sensor readings shows up that's far away from that normal cluster, the model flags it as an anomaly, a potential fault.
And it never needed a human to label anything as faulty. It just learned to spot what's different.
That's the power of it. It's pure discovery.
And this applies so well to business, too. You don't know who your customers are, but you know you can find groups within them.
Customer segmentation is the classic commercial use case. Telecom companies do this all the time with call detail records, or CDRs.
So call times, data usage, location, that kind of thing.
All of it. Without any labels like loyal customer or at risk of leaving, the unsupervised learning model just finds the natural clusters.
And you might find a group of, say, high data use night owls and another group of low data daytime professionals.
Exactly. And once you know those groups exist, you can stop sending them all the same generic marketing and create really targeted strategies for each one. It's incredibly effective.
And in finance, too, I imagine, where finding assets that behave similarly is key.
Absolutely critical. In financial portfolio selection, if you have thousands of stocks, you can't manage each one. Unsupervised learning helps by grouping assets based on how similarly their returns move over time.
So if two stocks tend to go up and down together, they get clustered.
Right. So the portfolio manager isn't juggling 500 individual stocks anymore. They're managing maybe 20 core clusters of similar assets. It just dramatically simplifies risk management.
Okay. So we have learning with a teacher supervised and learning by just finding patterns unsupervised. Now let's get to the most complex and I think most interesting one, the one that's all about making decisions.
Reinforcement learning, or RL. This is where an agent learns the best way to behave through direct interaction with its environment.
So unlike the other two, which are kind of passive data processors, an RL agent has to actually do things.
It has to take actions. The whole idea is really inspired by the most basic concept of trial and error.
This feels like the most human way of learning. It's like teaching a dog a trick. You don't show it a diagram, you just reward it when it does something right.
And you ignore it or penalize it when it does something wrong. That continuous feedback loop is what defines it. To make it all mathematically solid, RL is formalized using something called the Markov decision process, or MDP.
The MDP. Okay, that sounds like the engine room of the whole thing.
It is. It defines all the rules of the interaction.
So let's break that down. What are the key parts of an MDP?
There are 5 main components. First, you have S, which is the set of all possible states the agent can be in. You know, its position on a chessboard, the temperature of the room, anything that describes the world.
Okay, the state of the world.
Yeah.
Then you have actions.
Right. A, the set of actions the agent can take. Move left, turn up the heat, buy a stock.
And then the physics of the world, how the world responds.
That's the third and most critical piece. The state transition probability function, P. This defines the environment's dynamics. It tells you, if I take action as in state S, what's the probability I'll end up in the next state S?
Wait, hold on. Why a probability? Isn't it just cause and effect?
Not always. In a simple game, like chess, maybe. But in the real world, things are stochastic. They're random. If you're an autonomous car and you press the accelerator, your final speed depends on wind, road conditions. There's an element of chance. The MDP has to account for that.
Ah, okay. So it assumes the future only depends on where you are now and what you do now, not how you got there.
That's the Markov property, yes. It simplifies the world just enough for us to be able to model it.
Okay, states, actions, probabilities. What's next?
The feedback.
The feedback. That's the fourth part, the reward function, R. This gives the agent an immediate reward or a penalty for taking an action in a certain state. It's the dog treat. Or the little zap.
And the final piece must be about long-term thinking, right? Weighing a small treat now against a huge jackpot later. Exactly. That's the discount factor, gamma. It's a number between 0 and 1. If gamma is close to 0, the agent is really short-sighted. It only cares about the next reward.
But if it's close to 1?
It's very far-sighted. It's willing to take a hit now for a much bigger payoff way down the line. Gamma basically controls the agent's strategic time horizon.
So the agent's ultimate goal is to find the perfect strategy, the optimal policy that gets it the most cumulative reward over time.
The maximum return, yes. And to do that, it needs to estimate the value of being in certain situations. That's where the value functions come in.
Okay.
There's the state value function, V, which tells you how good is it to be in this state. And then, more importantly, there's the action value function, Q.
The Q function. I've heard that term a lot.
The Q function, or Q value, is the key. It tells you the accepted return if you start in a state S, take a specific action A, and then follow your policy from there on out.
So if you can figure out the true Q value for every possible action in every state,
you've solved it. The best strategy is just to always pick the action with the highest Q value.
But this whole system immediately creates this fundamental dilemma, doesn't it? The trade-off between exploration and exploitation.
It's the central problem of RL. It's a universal problem, really. Do you stick with what you know works well, exploitation, or you try something new, exploration, that might be even better?
I think about it in business all the time. Exploitation is refining your current hit product. Exploration is that risky R&D project that could be the next big thing or a total flop.
It's the cash cow versus the moonshot. And the AI agent has to make that choice constantly.
So how does it do that?
Well, the simplest methods are things like epsilon greedy. The agent acts greedily, it exploits most of the time. It picks the action with the best known Q value.
Bucks sometime.
But say 10% of the time, defined by epsilon, it takes a completely random action. It explores. That brute force randomness just ensures it doesn't get stuck in a rut.
That feels a bit crude. Is there a more subtle way?
There is. Boltzmann exploration is more sophisticated. Instead of pure randomness, it chooses actions based on a probability distribution weighted by their Q values.
So better actions are chosen more often, but even bad actions have some small chance of being picked.
Exactly. And you control it with a temperature parameter. High temperature means more randomness, more exploration. Low temperature means it almost always picks the best action, favoring exploitation. It's a much smoother way to balance the two.
Are there even more targeted ways to explore?
Oh, yes. The more advanced directed methods are all about sample efficiency. They use statistics to guide the agent toward parts of the world it hasn't seen much of, or where its estimates are very uncertain. It's like purposeful curiosity.
And sometimes you can just build the need for exploration right into the reward itself.
You can. Using something called entropy regularized rewards, you basically give the agent a little bonus, not just for getting rewards, but for maintaining a bit of healthy randomness in its actions. It prevents the strategy from collapsing onto a single good but not great solution too early.
Okay, so once the agent starts interacting with the world, it has to decide how to use that experience. And this seems to be where the RL world splits into two big camps: model-based and model-free.
It's a fundamental split. It all comes down to whether the agent tries to build its own internal map or simulator of the world.
So model-based methods.
Yeah.
They learn the rules of the game.
They learn the rules. They learn the transition function P and the reward function R. This lets the agent plan. It can run what-if scenarios in its head without actually having to take an action in the real world.
Like a chess grandmaster thinking 5 moves ahead. Dynamic programming is a classic example of this, right?
It's the foundational model-based approach, yes. It requires a perfect model of the world, and then it can compute the optimal strategy just by thinking about it. No real-world interaction needed.
But most real-world problems are too complex to have a perfect model. You can't have a perfect model of the stock market.
You can't. And that's exactly why model-free methods became so popular. They just skip building a model entirely.
So they learn directly from experience.
Directly from trial and error. They learn the value function or the policy just by doing things and seeing what happens.
Let's talk about the big model-free breakthroughs then, starting with Q-learning.
Q-learning was a huge deal. It's what's known as an off-policy algorithm, and that distinction is everything.
Off-policy, meaning?
It means it can learn the value of the optimal policy, the perfect strategy, even while it's following a completely different, maybe even random exploratory policy.
Wow. So it can be stumbling around in the dark, exploring. But at the same time, it's learning what the perfect light-filled path looks like.
That decoupling gives it incredible flexibility. Now, you can contrast that with SARSA.
Which is on policy.
Exactly. SARSA is on policy. It learns the value of the policy it is actually following. If the agent takes a suboptimal exploratory step, SARSA learns the value of that suboptimal path.
So Q-learning learns the value of the fastest route to the destination, even if you're taking a scenic detour, while SARSA learns the value of the scenic detour itself.
That's a perfect analogy. And both of these are types of temporal difference, or TD methods.
TD methods.
The key idea with PD is bootstrapping. It updates its value estimates based on other estimates instead of waiting until the very end of an episode to see the final outcome. It makes learning much, much faster.
And that leads to more advanced versions, like TD lambda. That lambda parameter is important, isn't it?
It is. TD lambda uses something called an eligibility trace. Lambda controls how far back in time credit for a reward is assigned.
So if lambda is 0,
you get TD 0, and only the very last state gets any credit. If lambda is 1, it's more like a Monte Carlo method where the credit is spread evenly across all the states that led to the reward. Lambda lets you tune that balance.
And that's why it was so effective for that old chess program, Nightcap.
Exactly. Nightcap used a variant called TD leaf lambda. In chess, the reward winning or losing only comes at the very end of a long game.
It's a very sparse reward.
Extremely sparse. TD lambda was able to propagate that final win-loss signal all the way back through the hundreds of moves that led to it, rapidly improving its ability to evaluate board positions. It went from a decent player to a master-level player in just 3 days.
That's incredible. Yeah. But all these methods, Q-tables, TD learning, they work great for chess, a board game. But what about the real world? What about something like an autonomous car that's getting data from a camera? the number of possible states is.
It's effectively infinite. You can't build a table big enough. And that's the wall that deep reinforcement learning, or DRL, was built to smash through.
So DRL just combines RL with deep neural networks.
It does. It uses the neural network as a powerful function approximator. The network can generalize. It doesn't need to see every single possible state to have a good guess at its value.
And the big breakthrough here was deep Q networks, or DQN.
DQN basically took the idea of Q learning and just replaced the lookup table with a deep neural network. That's what allowed it to process raw pixels from screen and achieve superhuman performance on all those old Atari games.
But that created new problems, right? Neural networks can be unstable.
Very unstable. You get this issue called overestimation bias, where the network consistently thinks certain actions are better than they really are, which leads to bad decisions.
And the fix for that was double deep Q networks. DDQN.
DDQN, a really brilliant, simple fix. The problem in regular DQN is you're using the same network to both choose the best next action and to evaluate the value of that action.
Okay.
DDQN decouples that. It uses two networks. One network, the online network, picks the action, but a second, older, more stable network, the target network, is used to evaluate the value of that chosen action.
So by separating the choosing from the evaluating, you get a much more stable estimate.
You get a much more stable and less biased estimate, yes.
Right.
It dramatically improves performance and reliability.
Which is why we see DDQN being used in things like autonomous driving.
Exactly. For complex maneuvers like overtaking on a highway, you need that stability. And then you have other architectures like dueling DQN, which tackles a different problem.
Dueling DQN. What's the insight there?
Dueling DQN improves learning efficiency by splitting the network into two streams. One stream estimates the value of the state itself, VUSSA. How good is it just to be here?
Regardless of what you do.
Regardless of the action. The other stream estimates the advantage of taking a particular action, HSA, compared to the other actions available.
Why separate them?
Because in many states, the specific action you take doesn't matter that much. Think about cruising on an empty highway. By separating them, the network can learn the value of being on an empty highway much more efficiently without wasting resources trying to figure out the tiny differences in advantage between wiggling the steering wheel a little bit.
So it learns to recognize what's a good situation to be in first and foremost.
And that leads to much faster convergence, which is great for things like UAVs doing obstacle avoidance.
Okay, so we've moved past purely model-free methods now into hybrid approaches, things that try to get the best of both worlds.
Right. And DynaQ is the classic example here. It blends model-free learning with model-based planning.
How does that work?
So in one step, the agent takes an action in the real world and learns from it. That's the model-free part. But then it also uses that experience to update its own internal model of the world. And then it can run dozens of simulated imaginary steps using that model.
So it's practicing in its head.
It's practicing in its head, which is much faster and cheaper than practicing in the real world. This hybrid approach can dramatically speed up learning.
And then there's something called prioritized sweeping.
That's all about being smart with your computation. Instead of updating everything all the time, prioritized sweeping focuses on the surprising experiences. When something happens that leads to a big, unexpected change in value, that state gets put at the top of a priority list to be updated first.
Focus your learning where your model of the world was most wrong.
Exactly. It's just a much more efficient way to learn.
So we've built up this whole framework,
Right.
From simple labeled data all the way to these incredibly complex systems that can plan and learn from simulated experience.
And we can see RL's strength is just unparalleled in any problem that involves a sequence of decisions, where today's choice affects tomorrow's outcome.
We mentioned games, but it's worth saying again how powerful things like Monte Carlo tree search are.
Absolutely. MCTS, often combined with RL, is at the heart of modern game-playing AI. And for games with hidden information, like poker, you have specialized versions that can handle that uncertainty. It just shows how adaptable the core ideas are.
And in transportation, the stakes are obviously much higher.
They are. The DDQN methods we talked about are vital for the kind of precision and safety you need for autonomous driving. And for drones, the dueling DQN architecture gives you that faster, safer convergence for things like avoiding obstacles in a cluttered room.
And of course, finance.
Of course. RL is used for dynamic portfolio selection. Algorithms can learn not just which stocks are good, but the optimal sequence of trades to maximize wealth over the long term, constantly rebalancing and adapting to the market.
So RL is this incredible engine for strategy. But there's one final huge roadblock. the one that's stopping these things from being deployed everywhere. And that's interpretability.
This is the big one. This is where it all comes together. The deep part of DeepRL is what makes it so powerful. The network is complex enough to understand the world, but that exact same complexity is what makes it a black box.
We don't know why it made the decision it did.
We don't. The connection between the input from the car's camera and the output, the turn of the steering wheel, is hidden in millions of numbers.
And if a supervised model mislabels a cat photo, that's fine. If a DRL-powered surgery robot makes a mistake,
it's catastrophic. And for any of these high-stakes domains, medicine, autonomous systems regulators, and users and engineers need to know why a decision was made. We can't just accept the answer because the math worked out that way.
So the goal isn't just to build a smarter black box. It's to build one that can explain its reasoning.
That's the frontier. We have to be able to connect the policy back to understandable, verifiable rules. Until we can do that, the deployment of the most powerful DRL systems in safety-critical areas is going to be very, very constrained. The power has to be balanced with trust.
That really frames where we are right now in AI development.
It does. It shows that even with the most advanced math, the problems often come back to these really fundamental issues of engineering and human trust.
So we've gone all the way from the simple classroom of supervised learning, where every answer is given, to the detective work of unsupervised learning, and finally, to the strategic trial-and-error world of reinforcement learning.
They each solve a different kind of problem. SL gives us classification, UL gives us structure, and RL gives us optimal decision-making over time.
And what's really fascinating to me is how they're starting to blend together. We talked about them as separate things, but a lot of the most powerful systems today use, say, unsupervised learning to find good features in raw data.
And then they feed those clean features into a supervised or an RL system. They're not just existing side by side anymore. They're starting to really reinforce each other.
It's the convergence that really matters.
It is. And, when you think about that core trade-off in RL exploration versus exploitation, it's worth remembering that it's not just an algorithms problem. It's a human problem. It's the challenge of business strategy, of personal growth. When do you stick with the safe, proven path? And when do you take a risk on something new that could be infinitely better? That's a universal lesson, whether you're a person or a piece of code.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.